You know, all around us, things are constantly getting pushed and pulled by forces we can't even see. But what happens when you've got more than one force acting on the same object? Well, today, we're going to visualize the answer and show you how two completely different looking paths can lead to the exact same result. Okay, let's just dive right in. Take a look at this hook. It's being pulled in two different directions at the same time. Now, the hook doesn't feel two separate tugs, right? It just feels one single combined pull. Our job is to figure out what that one force really is. All right, so first things first, we gotta break this problem down. Before we can figure out the combined effect, we need to know exactly how strong each pull is and what direction it's going in. Okay, so here's what we're working with. Force number one is yanking with 600 newtons of strength at a 45-degree angle. And the second one, that's the heavy hitter. It's pulling with 900 newtons at a 30-degree angle. These are our two ingredients. So here it is, the big question. How do we mash these two forces together into just one? We're looking for what physicists call the resultant force. Basically, the single force that does the exact same job. And the really cool part? We can actually draw the answer. Let's kick things off with a classic approach, the parallelogram law. This technique is just brilliant because it takes these invisible forces and turns them into a simple shape that we can actually see and measure. The process here is actually super simple. First, you draw both force arrows starting from the same exact point. That's our hook. Now here's the magic. From the tip of each arrow, you just sketch a line that's parallel to the other arrow. What you're doing is building a little map of how both forces work together. And just like that, you've got a parallelogram and the answer is hiding in plain sight. And boom, there it is. See those dashed lines? They complete the shape. And that line cutting straight across the middle, the diagonal stretching from the start to the far corner, that is our resultant force, R. The length of that line is the combined strength, and its angle is the final direction. Now, the parallelogram method is awesome, for sure, but what if I told you there's another way to look at this, almost like a shortcut? This brings us to method number 2, the triangle rule. It might look different at first, but trust me, it's really the same idea in disguise. The big difference here is just how we arrange the arrows. Instead of starting them both at the same spot, we place them tip to tail. Think of it like taking a walk. You go along the first path, and the second you get to the end, you immediately start walking along the second path. No going back to the beginning. And check out what you get. We have our first force, and then tacked right onto its tip is the second one. The most direct route from where you started to where you ended up is that straight line, right? Well, that line is the missing side of our triangle, and yep, you guessed it, that's our resultant force, R. So we've built our shapes using two different methods. The geometry tells us they should give us the same answer. Now it's the moment of truth. What are the actual numbers? What's the final strength and the final direction? You know, the beauty of doing it this way is that if you draw everything carefully to scale, let's say you use 1 centimeter for every 100 newtons, you can literally just pull out a ruler and measure your answer. It's awesome. So first up, let's find the magnitude, the raw power. And when we measure it, the combined force smacking that hook is a whopping 1,391 newtons. But wait, that's only half the picture, isn't it? Knowing how hard it's being pulled isn't enough. We also need to know which way it's going. A force is a vector, after all. So, time to measure the angle. And that angle comes out to 47.8 degrees. So there you have it. The hook feels a single pull of 1,391 newtons at a 47.8 degree angle. That is our complete answer, problem solved. But, you know, just getting the answer is one thing. The really cool part, the big aha moment, comes when you see how our two methods are secretly the same thing. Okay, just look at them here, side by side. You've got the parallelogram on the left and the triangle on the right. See it yet? Look closer. The triangle method, it's not a different method at all. It's just a shortcut. Yep, that's it. The tip-to-tail triangle is literally just one half of the complete parallelogram. They aren't two separate ideas. There are two ways of looking at the exact same geometric truth. It's so simple, but so powerful when you see it. And really, that's the big takeaway here. This whole graphical approach is amazing because it takes something abstract and invisible, like a force, and turns it into a simple shape that our brains can instantly understand. You're not just calculating, you are literally seeing the physics happen. Which leaves us with one last thought. Yeah, today we just solved for a simple hook, but this same principle is at play absolutely everywhere. It's in the tension of a suspension bridge's cables, the lift on an airplane's wing, the thrust of a rocket. So next time you see something being pushed or pulled, try to imagine the hidden geometry, the invisible triangles and parallelograms that are defining the outcome.